Now we go to see the slope that creates intelligence. The slope that creates intelligence. So here we'll be looking at ideas like derivatives, gradients, and optimization. Of course, we already got talking about that in previous videos. So, and the objectives here will be to understand what the slope represents. We saw in gradient descent, right? We saw the idea of slope there. So this is us digging into that whole concept. We compute derivatives of single variable functions. So here we are going to say the mathematics, really. Then compute gradients of multivariable functions. So when you have more than one variable, of course, we know AI systems are usually they have multiple parameters. Then explain why the gradient points in the direct explain why the gradients point in the direction of steepest increase, then apply derivatives and gradients to optimization problems, then understand how gradient descent powers modern artificial intelligence, and implement derivatives and optimization using Python. So let's see why the slope creates intelligence. Imagine standing on the side of a mountain. I mean, the kind of thing we said in the illustration we gave in the last video. You want to reach the lowest point in the valley without a map. How do you know which direction to walk? So you simply look for the steepest downhill direction. Then nature performs optimization in exactly this way. So artificial intelligence follows the same idea. Instead of mountains, AI has a loss function. So it's more like there's a loss function mountain that you want to keep climbing down so you get to the smallest loss, which is like somewhere in the valley. So instead of walking downhill, AI updates its parameters. Instead of gravity, AI follows the gradient. So the ability to continuously improve by following the slope of a function is one of the central ideas behind machine learning. So intelligence emerges by repeatedly moving in the direction that reduces error. So repeatedly moving in the direction that reduces error. So, and then you have that improvement going until you get what you want. So question is, what is a derivative? So derivative measures how quickly a function changes with respect to its input. So, that's where the idea of dy dx comes from, or df dx. So dy dx is the rate at which y changes with respect to x. So suppose f of x is x squared, for instance, the derivative is written as f prime of x, or df dx. Thanks to people like uh Leibniz and who else? I've forgotten the other person. Is it Leibniz and Newton? I think it's Isaac Newton and Gottfried Leibniz, yeah. So they gave us the present representation for derivatives. So it's this df/dx simply represents the slope of the tangent line at any point on the curve. So if the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. If the derivative is zero, the function may have reached a maximum, minimum, or saddle point. So how do you compute derivatives? Of course, that's calculus. Consider the function f of x equals x squared. Using the power rule, d dx of x raised to power n is n x raised to power n minus 1. So we obtain f prime of x to be 2x. Suppose x is 3, then it means that then you can then say the slope evaluated at 3 is equal to 6. So f prime of 3 is 2 times 3, which is 6. So this means that near x equals 3, every increase of 1 unit in x increases the function value by approximately 6 units. So here it means that for every unit of increase in x, the function itself is increased by 6 units, because that's what the slope tells us. That is near x equals 3. Example, differentiate f of x. Differentiate f of x equals 5x cubed plus 2x squared minus 4x plus 1. So differentiate each term separately. So d dx of 5x cubed, you get 15x squared. For 2x squared, you get 4x. For minus 4x, you get minus 4. For 1, which is constant, you get 0. So it means that f prime of x, when you have this, is 15x squared plus 4x minus 4. And that's it. So you can then evaluate at some point. Say, if you want to evaluate at x equals 2, so you just substitute 2 here. That's 15 into 2 squared plus 4 times 2 minus 4. That's 15 times 4, 60. 4 times 2, 8 minus 4. So 60 plus 8 is 68 minus 4. That's 64. So the function is increasing very rapidly at x equals 2. Like that. So we can, of course, compute that using SymPy. In fact, if you want it to appear beautifully, it's better not to use a print function. So, with print, it is written like in Python format. But without the print function, you're going to see it like in the proper outputs you should have when you use something like LaTeX. So that's what we are going to have in a moment as that finishes rolling. Yeah, so we have 15x squared plus 4x minus 4, just like what we have up here. Okay, so then we have numerical approximation of derivatives. Sometimes we cannot compute derivatives symbolically. Instead, we approximate them using the difference quotient. So f prime of x is now approximately f of x plus h minus f of x all over h, where h is a very small number. As h approaches zero, then the approximation becomes more and more accurate. So as h becomes smaller and smaller, the approximation becomes really accurate. So imagine we want we define the function x squared and we want to evaluate it around 3 with a very small h that is 10 raised by minus 6. So the derivative, of course, is f of x plus h minus f of x all over h. Then you can then print that derivative. So we run that and we have something like 6. So, the other time when we did this, this corresponds with this problem of 6. But here you can see there's a little error there, and that's what numerical stuff is about. So if you make the error small, like say 10 raised by minus 0, 10 raised by minus 10, you can see I think it should be it's getting closer and closer, right? Let's say 10 raised by minus 100. Okay, so you can see perfect zero here is what you end up getting. Okay, I think that's too much, right? So because we should have like the answer should be 6. So that's what we have. So from derivatives to gradients, now let's look at this. Many real-world problems depend on several variables. Instead of f of x, we work with f of x comma y, or even f of x1, x2, all the way to xn. The derivative generalizes to the gradient. So the gradient is simply a vector containing all the partial derivatives of a function. So when you have the gradient, it's like all the partial derivatives are embedded in that when you have more than one variable. So for a function f of x comma y, the gradient is simply grad f, which is partial f partial x and partial f partial y, like that. So imagine example of a gradient. Consider the function f of x comma y equals x squared plus y squared. Compute the partial derivative. So with respect to x, you have partial f partial x, that's 2x. Y is constant in that case, so it's 0. With respect to y, x is constant, so when you differentiate x with respect to y, that's 0. Differentiate y squared, you get 2y. Therefore, the grad f is 2x comma 2y. So the gradients point towards the direction of steepest increase, usually. So interpreting the gradient, now imagine if you suppose that x comma y is 3 comma 4, then so going by the gradients we got here to be 2x and 2y. So if you substitute x and y to be 3, 4, you have 6 comma 8. This vector tells us the direction in which the function increases most rapidly. So if we instead move in the opposite direction, we have minus 6, minus 8. The function decreases most rapidly in that direction. So this simple idea forms the basis of gradient descent, which we've been talking about a lot. I will keep talking about it because it's a very core idea, in minimizing loss in AI. So example, find the gradient of f of x comma y equals 3x squared plus xy plus 4y squared. So if you differentiate with respect to x, you get 6x here you get y, and here you get nothing because there's no x. If you differentiate with respect to y, you get 0 here, you get x here, and here you get 8y. Therefore, the grad f is now 6x plus y comma x plus 8y. So if you evaluate at say 1 comma 2, so put 1 for x and 2 for y. So 6 times 1 plus 2, that is 8 here. Then 1 plus 8 times 2, that is 1 plus 16, which is 17. So grad f evaluated at 1 comma 2 is 8 comma 17. So we can also compute that right here. So you have using SymPy, that is. So x, y are the symbols. So you have x squared, y squared, and then you compute the grad. So this is what it gives you. But if you want to have something neater, you can remove the print when you work with SymPy. So it gives you, oh, okay, it's still showing the same thing. This will be more beautiful. It's okay then. So you have 2x comma 2y. The grad is actually defined by the derivative SP differentiator. That's you have the diff function from SymPy, so f comma x. So it means you are differentiating the function f with respect to x. And SP dot diff the function with respect to y. So you get 2x 2y like that. So if you try it for 3x squared plus xy plus 4y squared, okay, 3, say f is equal to 3x, that's 3 times x raised to power 2 plus xy plus x multiplied by y plus 4y squared. That's 4 times y raised to power 2. So if you mute this and you do this, you also get 6, you get a 6x plus y, 8x plus 8y. 6x plus y, x plus 8y that we have here. So anyhow you want to do it. Now, question is, why does AI need gradients? So why AI needs gradients? Suppose the machine learning model makes a prediction. The prediction contains some error for sure. So the error is measured by a loss function. For example, let the loss function be L of W, which is equal to W squared, where W is a model parameter. So the derivative of W is actually the LDW, which is 2W. And suppose that W is equal to 5. So the LDW is now equal to 10. So the LDW is equal to 10. Since the derivative is positive, decreasing W will reduce the loss for sure. So the parameter update rule is now W new is the old W minus eta multiplied by the LDW. So where W is the current parameter, we've learned about slope already, the LDW, you already know it tells you how fast or how slow things happen. So W is the current parameter, eta is the learning rate, the LDW is the gradient, which we've been talking about. And then that reminds us of the idea of gradient descent once more. So again, we talk about gradient descent. So mathematically, we have theta nu. Okay, I mean, we've talked about yeah, mathematically, we have theta nu equals theta minus eta grad L of theta, where theta represents all model parameters. Eta is the learning rate, and grad L is the gradient of the loss function. So the loss function then is given as if can now be given as a mathematical function, and then we apply the whole idea of calculus to it. So minimize f of x equals x squared, for instance. The derivative is f prime of x, which is 2x. If we start with x equals 6 and choose eta to be 0.1, then the object rule becomes x new equals x minus 0.1 multiplied by the gradient, which is 2x. So you have that function to be x minus 0.2x. So starting doing the iterations now, iteration 1, when x is 6, you have 6 minus 1.2. That's 6 minus 0.1 times 12. That is 6 times minus 1.2, which is 4.8. Next, you have 4.8 minus 0.1 times 4. I mean 0.2 times 4.8, that's 0.96, you get 3.84. That's second iteration. Third iteration, you have 3.84 now, minus 0.2 times 3.84, you get 0.768. That gives you 3.072. And it keeps going like that. Notice that the values move steadily towards zero. Now, the value will move towards the minimum value of x squared. And if you plot x squared, the minimum point is x equals 0. So if you keep going, it gets you to x equals 0, which is the minimum of the function. So the lowest loss will correspond with the lowest point of the function you are minimizing. So imagine, so if you do it using code, then you can easily visualize. So x is 6.0, learning rate is 0.1. For I in range 10, that's from 0 to 9. So the gradient is 2 multiplied by x, as we know. So the function now is equals x minus learning rate times gradient. So you print iteration and all that. So you start with 4.8, and then in 10 steps, you have moved to 0.6. So it's going that fast. So imagine if I do 20, so 20. I mean, 0.6 is already close to zero enough. So in 20, okay, we're still somewhere here. So it's now 0.0692. So let me say do 50, for instance. 50. So 50, you see, okay, we're almost there, like almost getting zero in totally. So I think before we get to 60, we should already have zero for 4 decimal places. So yeah, okay, we start having starting from the 53rd iteration. So if you have more decimal places, you need more iterations to get all zero. So it all depends on what exactly you might want. So you can always play with this number. So let me take it back to 10 that was there initially. Okay, so now having talked about that, we can then do gradient descent in 2 variables. So what we did up there was for 1 variable. What about 2 variables? Consider f of x comma y, which is x squared plus y squared. The gradient is grad f, which is 2x comma 2y, which we know already. Suppose we begin at 4 comma 5. So the gradient will be 2 times 4, 8, 2 times 5, 10. So using a learning rate of eta, which is 0.2, what do we do? The updates then become, for x, we have x equals 4 that is the initial value, 4 minus 0.8, the 4 we started with, which 4 minus the learning rate 0.1 times 4. No, 4 minus 0.1 times the gradient, which is 8. So you have 4 minus 0.8, which is 3.2. For y, you have 5 minus 1.0. That's 5 minus 0.1 times 10. 0.1 times 10 is 1, so you have 4 there. So the point moves. So if you keep doing that, and then the point moves closer and closer to 0, 0. And that's what we expect for x squared, y squared. So which is the minimum of the function. So yeah, you can get the minimum of this function by differentiating and seeing all that. Now, we can do, so x is y, x is 4.0, y is 5.0, the learning rate is 0.1. So for I in grad 10, so you do the grad 2x and 2y, and then you have x, so it keep reducing. So the new x is the old x here, minus equal to means the repeated process. So the old x minus the learning rate times the gradient of x, then the old y minus the learning rate of the gradient of y. Okay, so and then you keep on like that, you print all the iterations. So it starts from 3.2, 4.0 that we have here, 3.4.0, and it keeps going. So you see it's reducing. So like I did before, if I do 20 iterations, for instance, so it's moving to 0.0461, and this is 0.5. So what if I do 50, like I also did before? Let's do 50. So for 50 now, okay, we are already getting the 0.00 is already showing. So it means that by say 55, we would have got all zeros. That's for 4 decimal places, though. If you have like 6 decimal places, we need to go more steps. In fact, zero starts showing at step 52. You have all zeros there. So that's the number of steps you need to take to get to that point. So that's how it is for multiple variables. Now we have applications of derivatives and gradients. Derivatives and gradients are used throughout science and engineering. So we see it's used in artificial intelligence, talking about training neural networks. Then for machine learning, the loss minimization, which we've been talking about, robotics, for motion planning. Then for computer graphics, you want to optimize surfaces, surface optimization. In economics, profit maximization, and even maybe cost minimization. In engineering, we have optimal system design. In making a car, for instance, have you ever wondered why cars look like fishes or birds, or aeroplanes look like a bird like that? So it's because the surface is optimized. So these things are patterned after nature, because even God in His creation has actually made it designed everything in such a way that they perform optimally, and then engineering can take a cue from all of that. In physics, also we have velocity and acceleration. So, derivatives and gradients can help us to understand velocity and acceleration. In finance, we have portfolio optimization, and then in medicine, you have medical image reconstruction. So, derivatives and gradients can be applied in all these senses. And then we go to summary. In this lesson, we learned that a derivative measures the instantaneous rate of change of a function. And a gradient extends derivatives to functions of many variables. So the gradient points toward the direction of greatest increase. Moving opposite the gradient decreases the function most rapidly. Gradient descent is an iterative optimization algorithm. And then modern machine learning and deep learning systems learn by repeatedly computing gradients and updating parameters according to theta nu equals theta minus learning rate times the gradient of the loss function. So for simple regression models to modern from simple regression models to modern large language models, optimization through gradients is one of the mathematical foundations. So, optimization through gradients is one of the mathematical foundations of artificial intelligence. Optimization through gradients. So, we come to our practice problems as usual. Um, so again, I'm going to be taking care of two of these problems. Now, in this case, I'll be dealing with problems 13 and 16. Problems 13 and 16. So this one says differentiative of x equals 7x raised by 4 minus 5x plus 9. Straightforward, 28x cubed minus 10x plus minus 10x. This is constant, so it goes away. So differentiate 4x raised by 5 minus 3x plus 8 minus 8. This is 20x raised by 4 minus 9x raised by 2 plus 1. So this is gone. Differentiate this. Of course, this is square root of x, which is x raised by half. That's half x raised by minus half. So that's what like 1 over 2 root x. So differentiate for fx equals 5 over x. That's 5x raised by minus 1, which is minus 5x raised by minus 2. That's 5 over minus 5 over x squared. So you see, you can see problems 1 to 5 here, 1 to 5, then 6 to 10. You can see 6 to 10 right here, 6 to 10. Then we have 11, see 11 to, okay, you can see 11 to 14, all of that here. 11 to 14. Okay, 11 to 14. Or let me make, okay, yeah, let's leave it at 11 to 14, yeah. 11 to 14. Then 15 to 17. 15 to 17. 15 to 17. And then I think the rest, some Python applications now. So, like I said, I'll be dealing with questions 13 and 16. 13 says, use the derivative to determine the critical point of f of x equals x cubed minus 3x squared plus 2. And 16 says, starting from x comma y equals 3 comma minus 2, perform one gradient descent update, just one, for f of x comma y equals x squared plus y squared using eta equals 0.1. Then, of course, if you want many more steps, you can do more iterations using programming like that. Of course, we can do it manually, but programming makes it faster. So let's do problem 13 and 16, and this will be done. So problem 13 says use the first derivative to determine the critical points of f of x equals x cubed minus 3x squared plus 2. So this is normal calculus stuff, right? But then in the context of loss function, it makes more sense. So we know that a critical point occurs where f prime of x is equal to 0. So we know that. So in that case, it means that we need the derivative of f prime of x, the derivative of f of x. So then we go on to do that. So we know that f of x is x cubed minus 3x squared plus 2. So that implies that f prime of x is equal to 3x squared minus 6x plus, okay, 3x squared minus 6x, that's all. That's 3 times, bring down the 3, reduce the power by 1, then 2 times 3, 6, then it reduce the power by 1. So we have f prime of x is 3x squared minus 6x. So what we then do is we equate to 0, equate to 0. So we have 3x squared minus 6x equals 0. Then we can solve. So 3x is common. 3x into x minus 2, yeah, equals 0. So that means we have 3x equals 0 or x minus 2 equals 0. That means that x is equal to 0 over 3 or x is equal to 2. So that means that x is equal to 0 or x is equal to 2. So these are the two values, the two critical points we have. So we know that these are the critical points. These are the critical points. Well, I mean, when you talk about a point, right? Um, we need the function values, right? Because x is not on its own. So to find the corresponding function values. So At x equals 0, for instance, at x equals 0, we know the original function is, we can recall that, right? The original function is f of x equals x cubed minus 3x squared, x cubed minus 3x squared plus 2. So we know that f of 0 would just be 0 raised to power 3 minus 3 into 0 squared plus 2. That is 0 minus 0 plus 2. And that is simply 2. So there we have, so if you want to put x and f of x together, that's like 0, comma 2. Or I mean that's also similar to x comma y if you want. If you like x1, y1. Then at x equals 2, at x equals 2, we have f of 2 to be 2 cubed minus 3 2 squared plus 2. That's 8 minus 12 plus 2. So that is minus 2. So again, we have 2 comma minus 2. X is 2. F of x is minus 2. Okay. So we have critical points. We have critical points 0, 2, and 2 minus 2. So then, using the second derivative, so second derivative helps us to know whether it's which one is minimum, which one is maximum. Using the second derivative, of course, we know the first derivative again is x cubed minus 3x squared plus 2. Then first derivative of that is like we got before. I don't have to do this again. I'm just doing that. So f prime prime of x is second derivative. That is 6x minus 6. Like that. So this second derivative now helps us to determine the nature. So this helps to determine the nature of critical points. By nature, I mean whether which point is minimum, which one point is maximum, or it's a saddle point. Nature of critical points. Okay, so how do we take care of that? So we evaluate f prime prime of x, which is 6x minus 6 at each critical point. Okay, so when f prime prime of x star, so if f prime prime of x star, that is the critical point now is that x star, right? So if, okay, let me do this now. If f prime prime of x star is less than 0, we have a maximum point. We have a maximum point. So less than 0, maximum point, greater than 0, minimum point. So if f prime prime of x star is greater than 0, we have a minimum point. Like that. So let's do this. At 0, comma 2, right? At 0, comma 2, we have f prime prime of, this is x1, y1. So it is the x we substitute. So we have f of 0. So f of 0 will be, 6x minus 6. So that will be 6 times 0 minus 6. So that is 0 minus 6, and that is minus 6. So since f prime prime of 0 is equal to minus 6, and that is less than 0, so 0, comma 2 is a maximum point, or you can say it's a local maximum. So for the other one now, at at 2 comma minus 2, the other one we got the other critical point. At 2 comma minus 2, we have f prime prime of 2. It's the x value you want, x2, y2 now. F prime prime of 2 is now 6 times 2 minus 6. So that's 6 times 2, 12 minus 6. So that's 6. So we can then say since f prime prime of 2 is equal to 6, which is greater than 0. So, okay, then 2 comma minus 2 is a local minimum. I mean, you can demonstrate that graphically in using something like Desmos. So all you just need is to plot the function itself. By plotting the function, you can easily read off all the local maximum or local minimum. So we have x cubed, x raised to power 3 minus 3x raised to power 2 plus 2. Okay, so if you point at this, is the 0, 2. So it's a maximum, it's at the top, so it's a maximum point. Then 2 minus 2, that's minimum point. That's what that simply tells us there. So that ends problem 13. So we go on to problem 16, which involves two variables. So problem 16. So starting from x comma y equals 3 comma minus 2, perform one gradient descent, just one gradient descent update for f of x comma y equals x squared plus y squared using eta equals 0.1. So the solution, first compute first you have to compute the gradient. So what you just call derivative, in the other case it's gradient here because you have more than one variable. So again, you have f of x comma y equals x squared plus y squared. So the grad of f will be partial f, partial x, comma partial f, partial y. So that means you differentiate with respect to x, that's 2x, with respect to y, that's 2y. And that goes. So we then evaluate at the gradient, evaluate the gradient evaluate the gradient at 3 comma minus 2. So we have grad f. So graph f of 3 comma minus 2 will just simply be 2 times, that's 2 times 3 comma 2 times minus 2, which is equal to 6 comma minus 4. So we have this. And then we do the gradient descent update. So the gradient descent update, the gradient descent update rule is, so we can have x new comma y new is equal to x comma y minus eta multiplied by the gradient of f, like that. Then we substitute the given values. So substituting the given values, we have x new and y new. So x new, y new. The new x and the new y are 6 no, they are 3 and minus 2. Okay, the old, yeah, they are the old. 3 and minus 2 are the old actually. So because we need x new and y new. So x new, x new, y new is equal to x old, y old, which is 3 comma minus 2 minus 0.1 multiplied by 6 comma minus 4. That's the gradient we got up here. So we can do this. So x new, y new is equal to 3 comma minus 2 minus 0.1 times each of that as 0.6 minus 0.4. So we then have x new, y new to be 3 minus 0.6 comma minus 2 minus 0.4. So that we then have x new, y new to be 3 minus 0.6, that is 2.4. Then minus 2 minus 0.4, that's minus 2.4 also. Is that correct? This is minus 2 here. So this is minus 2 minus minus. So it's minus minus, sorry. Minus 2 plus 0.4, that's minus 1.6. Minus 1.6 like this. So yeah. So that simply tells us that x new is 2.4 while y new is minus 1.6. So we can go again and do the whole process again, but we need just, the question says to do one update. So so you see the old was so this one moved from 3. The old was it's from 3 to 2.4, and then the other one moved from minus 2 to minus 1.6. So like that. So we can continue. So if we continue, right, we see that the new point is closer, it is closer to 0, 0, which we expect the whole thing to converge. That 0, 0 is the minimum, which is the minimum, of the function. Yeah, and that ends this one. So in the next video, I think we'll be dealing with gradient descent or something. So just watch out for that. Uh, Gradient descent proper. So with these questions, we are done with this video. I'll just flash the problems once again so you can try your hands on them to see if you really get the gist. So here you see problems 1 to 5 clearly. Problems 1 to 5. Then 6 to 10. 6 to 10. 11. You can see 11 to 15 here. Or let's say 11 to 14. 15 is not showing fully. So 11 to 14. Then 15 to 17. And the rest. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you haven't subscribed, this is your opportunity. Why not go ahead and hit the subscribe button and the notification bell also, so you can always get alerted each time a new video is released. Having done that, you can become a member of this channel by clicking on join. That gives you some special privileges to find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.